SwayamPrabha. Digital India. Educated India.
Now, whatever the concept we have learned from the last few lectures, we'll apply them to the aircraft system. How we can find the transfer function for the different approximations, longitudinal motions or in the lateral direction motion, how we can come up the transfer function. We'll study them in this lecture. So aircraft transfer function. The main motivation of having the transfer function for the aircraft systems are to apply the linear control or classical control theory to the system, because this course mainly we are studying the classical control concepts. So let's start with the first short period dynamics, what you have arrived before, short period. And how we can find the transfer function for the system, we will discuss here. The short period approximations with control held fixed was, it means without the control, the natural dynamics for the short period motion, we had delta alpha dot delta q dot equal to g alpha divided by u naught 1 m alpha plus m alpha dot g alpha divided by u naught m q m alpha dot, and the state vector we had del alpha del q. So this is a natural system, natural linearized motion, natural linearized equation without the control. So now, if you consider now, if the equation in the system are affected by control input from the elevator, then we can modify this equation. Now, the equation with control input from the elevator in state space form I'm rightly writing the equation, but if you want to see how it is coming, you can go back to the longitudinal motion dynamics, linearized motion dynamics, and we can see how it is coming. So we had the same delta alpha dot delta q dot equal to g alpha divided by u naught 1 m alpha plus m alpha dot g alpha by u naught m q plus m alpha dot del alpha del q, and the contour here we had B matrix which is having the components G delta E, M delta E plus M alpha dot G delta E divided by U naught into delta delta E. So here we are assuming the force from the propulsion system is assumed to be 0 for the simplicity. So let me write control due to propulsion system is neglected for the simplicity. If you notice, so this is my x dot, this is A matrix, this is X, this is B, and this is U control. So this A is the system matrix, B is the control matrix, and U is the control input for the system. And from this equation, let me define this equation number 2, and this is equation 1. So from equation 2, we can get 2 OD. The first, let me write the first OD for the system defined by equation 2. We have the following ODs. The first equation, delta alpha dot equal to, we can write G alpha divided U naught and delta alpha plus delta Q plus G delta E, capital delta E. And second OD equation, second OD, delta Q dot equal to M alpha plus M alpha dot G alpha U naught delta alpha plus MQ plus M alpha dot del Q, and the term due to the control M delta E plus M alpha dot G delta E U naught and capital delta E. Let me define this equation number 3, and this is equation number 4. We will take the Laplace transform. Let's start with the equation 1 and we apply the Laplace transform to the equation, not equation 1, equation 3. And taking Laplace transform, for the first equation yields S delta alpha S equal to G alpha U naught alpha S plus delta QS plus delta E U naught delta delta E. Yes. And from this equation, we can further write S minus G alpha U naught capital alpha S minus del QS equal to G delta E U naught capital delta ES. And similarly, if you apply the Laplace transform to the second equation, please note that we are assuming the initial condition to be 0. We are assuming that the system is in the equilibrium point. So initial condition we are assuming to be 0. Similarly, for the fourth equation, for the fourth equation, if you apply equation 4, applying Laplace transform yields, we can write is delta QS equal to M alpha plus M alpha dot G alpha U naught delta alpha S plus MQ plus M alpha dot delta QS plus m delta E m alpha dot u naught j delta E into capital delta E S. And if you further simplify, you can write minus m alpha plus m alpha dot g alpha divided by u naught capital alpha S plus S minus mq plus m alpha dot delta qs equal to, we can write m delta E plus m alpha dot divided by u naught and j delta E into capital delta ES. And let us define this equation number 5. This is equation number 5 and this is equation 6. Now if you divide equation 5 and equation 6 by delta ES, so dividing, the same concept we are applying what you have done for the brute force method or the where you have applied the Cramer's rule. So same concept will be applying here, or you can go with the general concept, the C SI minus A inverse B. These are same concept we can apply. If you want to find the delta alpha S with respect to delta ES, or if you want to find delta QS with respect to delta DS. So here we have to modify the B and C matrix and we can find the transfer function. But here we are applying the brute force method, what we have done in the previous lecture. So we're dividing equation 5 and 6 by delta DS, we get S minus G alpha divided by U naught delta capital delta alpha is divided by delta ES minus delta QS divided by delta ES equal to G delta E divided by U naught. And for the equation 6, this is equation 7. And for equation 6, we'll have and minus m alpha plus m alpha dot g alpha divided by u naught delta alpha is and delta ES plus S minus mq plus m alpha dot delta QS divided by delta ES equal to m delta E plus m alpha dot g delta E divided by u naught. And let us define this equation number 8. From equation 7 and 8, we can arrange the equation in matrix form. So we obtain a set of algebraic equations in terms of transfer functions delta alpha is divided by capital delta ES and delta QS divided by delta ES. And in matrix form, we can write S minus G alpha divided by U naught minus 1 minus M alpha plus M alpha dot G alpha divided by U naught S minus MQ plus M alpha dot, and the transfer function delta alpha S divided by delta ds and delta qs divided by capital delta s equal to j delta e divided by u naught m delta e plus m alpha dot g delta e u naught. So the matrix form. So here you can apply the Cramer's rule. So let's denote A matrix. This is X matrix and this is B matrix, for example. So here, if you want to use Cramer's rule, here we can use to find delta alpha s divided by delta es or x1, and because here x is the vector, so here x we can write x1 x2. So x1 basically delta alpha is divided by delta es, and x2 which is delta qs divided by delta es, or it is x2. So through Cramer rule, x1 you can find determinant a1. So here a1 is this is the first column, this is the second column. So a1 b divided by determinant a, and x2 we can find a2 b divided by a determinant. This is how I can find. So let's first find the determinant a. So here basically is minus g alpha u naught minus 1 minus m alpha plus m alpha dot g alpha divided by u naught. Fourth term is minus mq plus m alpha dot. And if we take determinant of this, we have s square minus mqs minus m alpha dot s minus g alpha u naught s plus g alpha divided by u naught mq plus g alpha u naught m alpha dot minus m alpha minus m alpha dot u naught g alpha. So here this both term can be cancelled out, they are same, and from this we can get the determinant s squared minus mq plus m alpha dot plus g alpha divided by u naught s plus g alpha divided by u naught mq minus m alpha. This is the determinant of a matrix, and now we'll find both the cases the numerator part. So denominator part is we have done. For numerator, so we'll find a1 b equal to, we can form the matrix G delta I U naught minus 1 M delta I plus M alpha dot G delta I divided by U naught S minus M cube plus M alpha dot, and it is the determinant will have S G delta I U naught M cube G delta I divided by U naught M alpha dot G delta I divided by U naught plus M delta I plus M alpha dot G delta I divided by U naught. And from this equation, we can further write, so both the terms, this terms cancel out. So we can write G delta I U naught is plus M delta I minus M Q delta I divided by U naught. The second numerator part, which is for the Q of S, we can write A to B. Here we can form the matrix S minus G alpha divided by U naught, G delta I divided by U naught minus M alpha plus M alpha dot U naught G alpha M delta I plus M alpha dot G delta I divided by U naught, and the determinant else to be is M delta I plus M alpha dot G delta I divided by U naught is minus G alpha M delta I divided by U naught minus G alpha U naught M alpha dot G delta I divided by U naught plus delta I divided by U naught M alpha and plus delta I divided by U naught M alpha dot G alpha divided by U naught. These two terms can be cancelled out because they are same. From this equation, we can further simplify M delta I plus M alpha dot G delta I divided by U naught into S plus delta I U naught M alpha minus G alpha divided by U naught M delta I. So using the above mathematics, we can find the transfer function now. So we have all the terms which can be used to find the transfer function. So using the above formulas, we can find x1 equal to delta alpha s delta delta s equal to, the determinant for both the cases will be remain to be same. So only part the numerator part, the denominator part will be same. So for x1 we can write a g delta I. So this part we can write g delta I plus m delta I minus, S is missing here, is g delta S m delta I minus m q delta I divided by U naught divided by the determinant part S square minus m q plus m alpha dot plus g alpha divided by u naught is plus g alpha mq divided by u naught minus m alpha. And the second transfer function x2, which is delta qs delta ds delta del s. So here the transfer function we can write. So the numerator part will be this one. This is the numerator part. So m delta e plus m alpha dot g delta e divided by u naught into s plus g delta e divided by u naught m alpha minus g alpha m delta e divided by u naught divided by the total determinant s square minus m cube plus m alpha dot plus g alpha divided by u naught into s plus g alpha m cube u naught minus m alpha. So if you notice here the stability derivatives, we can find constant for a particular flight regime. So in the both the transfer function will have the, in the numerator we'll have the function of s's, and in the denominator we have another polynomial which will be function of s's only. So if you are having this transfer function for both the system, we can design the control. This will be our plant. So for example, if you want to control alpha s, then delta alpha s divided by delta es. So whole the transfer function will come into this picture, and here we can design a control delta es which will give, and here this is the controller, and here we have the summing point, we have dgr alpha dgr, and we can get the feedback which is the output actually delta alpha s. This is negative feedback, this is positive. So this is how we can design the control system, and this concept already we have done in the first half of this lecture. So let's stop it here. We'll continue for the another system in the next lecture. Thank you.